Hey, welcome to the Explainer. Think of the periodic table, that big chart of all the elements. Well, what if I told you it's not just a chart, it's actually a map? And like any good map, it's got these hidden rules, these patterns that tell us something really fundamental, like just how big are atoms anyway? So let's dive in and start exploring this atomic map.
So that leads us to the big question, right? Is there some kind of pattern to the size of atoms? I mean, you'd think, logically, that as you add more stuff, more protons, more electrons, the atom would just, well, get bigger. Makes sense. But is it really that simple? Is there a secret, predictable pattern hidden right there in the periodic table? And the answer is, yep. There absolutely is a pattern. But, and this is the crazy part, it's probably not what you'd expect. It's totally counterintuitive. You see, when we move across a row, say from lithium over to neon, the atoms don't get bigger. They actually get smaller. They shrink. So what in the world is going on here?
Okay, but before we can even start to unpack that mystery, we have to ask a more basic question. How do you measure something you can't even see? To really get a handle on these trends, we gotta be on the same page about what atomic size even means to a scientist.
An atom isn't some neat little sphere like a marble. It doesn't have a hard edge. It's more like a fuzzy cloud of electrons, and there's no clear end to it. So how do you measure that? Well, scientists got clever. They came up with a really smart workaround. They take two identical atoms, get them to bond together, and then they measure the distance right between their centers, their nuclei. The atomic radius, it's just half of that distance. Pretty neat, huh?
And here's exactly what that looks like. You can see the two atoms side by side. You just measure that full distance between the two nuclei, and boom, half of that is your radius. It's a really elegant way to get a solid number for a fuzzy object. All right, so now we've got our ruler. Our map is ready. Let's start our journey. Okay, first up on our journey, we're going to travel south on our map. We're moving down one of the columns, what chemists call a group.
So here's our first rule for this map, and this one makes perfect sense. As you go down the table, the atoms get bigger. Simple, straightforward, intuitive. So far, so good, right?
Let's take a look. Here's sodium, or Na, which you'll find right below lithium, Li, on the table. And just like our rule says, you can see the sodium atom is way bigger. So the rule holds up, but why? Why does this happen? Okay, it really boils down to two main things. First, and this is the big one, every time you jump down to a new row, you're adding a whole new layer of electrons, a completely new shell. It's kind of like putting on another coat in the winter. You're just going to get bigger. And second, those inner layers of electrons act like a shield. They block the outer electrons from feeling the full magnetic pull of the nucleus. We call this the shielding effect, and it basically lets the whole atom puff out a bit.
All right, so we've got the down trend figured out. Easy enough. Now for the second part of our trip. And trust me, this is where our map gets weird and really, really interesting. We're going to move east, straight across a row, or what's called a period. And here's the puzzle. Think about it. As we move across a row from one element to the next, we are adding more stuff. We're adding a proton to the nucleus, we're adding an electron to the cloud. So common sense says it should get bigger, right? More stuff equals bigger size. But does it? And here's the shocker. The answer is a big, fat no. In fact, the complete opposite happens. As you move from left to right across the table, the atoms get smaller. Yeah, smaller. Let's actually trace this path on the map. We start with lithium here. Now we move one spot to the right to beryllium. It has more protons, more electrons, but look at that, it's smaller. And then we move again over to boron and it shrinks even more. So what's going on? What force is so strong that it's overpowering the fact that we're adding more material? Okay, here's the secret sauce. When you move across a row, you're not putting on a whole new coat. You're not adding a new electron shell. Instead, all those new electrons are just being crammed into the same outer layer. But at the very same time, the nucleus in the center is getting stronger and stronger because you're adding protons. So you've got this more powerful positive charge in the middle, and it acts like a stronger magnet,
pulling all of the electrons in tighter. That increased pull, what we call effective nuclear charge, is what makes the whole atom shrink. So let's recap. We have our two simple rules for the map. Bigger as you go down, smaller as you go across. Now let's zoom out and see what the whole landscape looks like when we put those two rules together. And there it is. This is what it all looks like. You can see our two rules playing out perfectly. Every time you see a huge peak, that's the start of a new row. That's when we add a whole new electron shell, so bam, the atom gets way bigger. But then, as you follow the line across that row, you see it go down, down, down. That's that stronger nucleus pulling everything in tighter, shrinking the atom, until you hit the very end of the row, the valley, where the atom is the smallest.
So, to put it another way, looking at this map, the highest peaks are always the atoms that have just one single electron sitting all by itself in a brand new outer shell. And the lowest valleys? Those are the atoms at the end of the row, the ones with a completely full outer shell, pulled in as tight as they can be.
Okay, just to give you a final, mind-blowing sense of scale here, I want you to imagine we could take the nucleus of an atom and blow it up to the size of a ping pong ball. Got that? Now, how big would the rest of the atom be? The whole thing would have a diameter of, wait for it, 25 miles. It is almost entirely empty space, all held together by these incredible rules we just talked about. So you see, the periodic table is so much more than just a boring list of elements you had to memorize in school. It's a map with an incredible amount of predictive power. We just figured out the rules for atomic size, and that leads to one last, really exciting question. If something as basic as size follows such a perfect, predictable pattern, what other secrets are hiding in plain sight on the periodic table, just waiting for us to find them?